Hi everyone. My talk is to discuss state-of-the-art parallel and distributed implementations on various high-performance computing platforms for processing remotely sensed big data. Nowadays, the amount of data with higher spatial and temporal resolutions and multiple structures available from remote sensing systems is increasing at an extremely fast pace. For instance, the amount of multi-temporal images extracted from ESA's Sentinel orbit has reached the petabyte level. As reported by NASA, the annual growth of remotely sensed data into Earth observing system data travel is more than 5 petabytes during 2018 to 2020, and is projected to increase to 47.7 petabytes by 2022. According to this ingest rate of data, the volume of data in Earth observing system is expected to grow to more than 246 petabytes by 2025. Considering their high volume and fast generation velocity, the processing of remote sensing data naturally becomes a big data problem. The challenges lie in data storage, management, processing, analysis, and almost every stage in the entire flow of today's remote sensing applications. We classify existing parallel solutions mainly into two categories: onboard data processing methods implemented on multiple GPUs, FPGAs, and the repository data processing methods implemented on clusters, grid computing platforms, and cloud computing platforms. For onboard methods, multiple CPUs offers parallel computing capabilities by multiple operations of remote sensing applications on multiple cores. GPUs have much more cores and are more powerful in parallel computing compared with CPUs. However, GPUs are not specialized in general-purpose computing. Effort has also been made in developing solutions on CPU-GPU platforms, in which GPUs are designated for parallel computing and CPUs are designated for general-purpose computing. FPGAs further enable configurable programming by which remote sensing algorithms can be adapted and executed in parallel according to the features of data. This onboard method may suffer from extremely long computation times when producing large-scale datasets. Clusters and grid computing platforms can integrate many computing nodes to enhance big data processing capabilities. As an evolution of previous developed techniques, cloud computing represents a natural solution to parallel and distributed processing of big data due to its advanced capability of service-oriented computing and internet-scale data storage. We provide in this table the comparison among different HPC platforms in developing parallel solutions. To summarize, onboard parallel techniques cannot fully cope with large-scale datasets due to limited computing resources. They are more applicable for real-time analysis of small data. On the contrary, repository methods are developed on platforms with distributed computing resources. They are scalable through the increasing volume of remote sensing datasets with high reliability. More importantly, with the support of visualization technology and powerful management utilities, cloud computing-based solutions are advantageous over other solutions in quick deployment and rapid elasticity. With this conclusion in mind, we concentrate on cloud computing architectures and investigate state-of-the-art technologies for parallelism exploitation. This is the fundamentals of the parallel processing mechanism in cloud computing, including distributed programming models, MapReduce, computing engine, Apache Spark, storage system, Hadoop distributed file system. Most cloud computing solutions focus on only exporting data-level parallelism by partitioning data and process them in parallel on cloud. Our recent work demonstrates the great significance of employing task scheduling techniques to further exporting task-level parallelism and during distributed data processing. A good schedule of task partitioning and assignment is beneficial for improving the utilization rate of the cloud system and reducing the execution time. The quality of schedule fundamentally determines the parallelism and the computational efficiency of remote sensing big data processing. Task scheduling is known to be anti-hard in many cases. Traditional strategies such as round robin and first come first service are straightforward and easy to implement, but these simple scheduling rules cannot cope with the complicated remote sensing data processing scenarios. Another category of scheduling strategies are heuristic methods. The key of a heuristic strategy is a deterministic rule that guides the searching procedure to exploit high-quality solutions. Heuristic algorithms are largely dependent on the initial solution and may easily suffer from local optima. Different from heuristics, meta-heuristics incorporate random search and local search during the solution exploration procedure to avoid being trapped into local optima. As a case study with a representative remote sensing application with a complicated processing flow for half-spectral image classification, we developed its parallel implementations on a Spark-based cluster system deployed with up to 32 nodes. The results on the left-hand side verify that the cloud implementation achieves similar classification accuracy compared with the serial version. However, as can be observed on the right-hand side, the cloud implementation achieves significant speed up over the serial method with all 32 nodes deployed on Spark. The speed up reaches more than 10. At this stage, we assume that no scheduling strategies are employed. We only use the distributed computing mechanism of cloud computing. We now show that scheduling strategies are necessary for enhancing the efficiency of cloud computing systems by exporting both data level and task level parallelism. The computation time can be further reduced by employing scheduling strategies. Also, the acceleration becomes more significant as the number of nodes increases. The two meta-heuristic algorithms, Horton-inspired evolutionary algorithms, and the particle swarm optimization both outperform the greedy search heuristic. The computational efficiency of QEA is slightly higher than that of TSO. Despite the extensive effort in developing parallel and distributed methods on cloud computing, there are still several challenging issues that must be addressed to fully facilitate the scalable and productive processing of remotely sensed big data, including standardization, data management, energy efficiency, smart platform integration, smart objective optimization, and orchestration, and so on. All right, this is my presentation.